talk in the hardware hacking village. There is the InfoSec career panel, so if you're interested in that, that is after this. Also after this in Lockpicking Village is another intro to lockpicking. There's of course another talk after this, but that's just other stuff going on. At 5 p.m. the demo party has been moved to the hardware hacking village, not the chill out room, but that's at 5 o'clock, hardware hacking village. If you're doing ham testing, that's at 6 o'clock in the lockpicking village. And then at 8 p.m. tonight is dinner and then board game night after that. And with a bit of luck, you won't ruin the experience for the kid having his high school graduation next door to us. You are dorks. Confirmed, dorks. No comment. Other than that, we have RtzqO with Git for Hackers.
God, that's loud. It's nice to know that this is a sound amplifier, and if I touch anything on this podium, it's going to be really noisy. So I'm going to try not to set this fine root beer down and do that. All right. So Git for Hackers. Of course, we'll get into the question of what this has to do with hacking in general in a moment, but thanks for taking some time out of the middle of your conference day to come to my talk. I am Jason RtzqO, or RtzqO, or RtzqO. And today what we're going to be talking about is deleting things, or the rather frustrating experience of attempting to delete things from the Git version control system, a system where record retention is in fact one of the only qualifying functional requirements. Tiny bit of lag. I think my laptop is so old that it's saying 1020, 1080p. Okay, now some of you maybe write software, and maybe some of you will never ever write a line of code. But if you know someone who writes software, or if you do write software, the chances are that you are at least aware of Git, and aware of the fact that over the last decade, it's kind of become the major de facto public repository standard. I remember when I started out doing software stuff, the field was a lot more cluttered as far as who was running what, but seeing a lot more centralization of Git. There's still a fair bit of SVN, but I think people are no longer seeing Mercurial as maybe the serious contender that it once was. And so we're seeing so much pressure around Git, and it's, you know, whether you're using GitHub or GitLab or Gerrit or Git or Fabricator or Redmine or something else I have never heard of, most of these platforms are centralizing on the Git service backend. And while Git is a fairly good distributed version control system, in my opinion, one of the best things about Git is that many of its users have no idea how it works. And since bugs and vulns by extension are essentially defined between the delta of expectation and reality, right? This is how I think things work versus this is what's actually going on. Hopefully you can see where I'm going with this. The more you understand about Git and the less someone else understands about Git, the more things you're going to take away from them. So to prove this point, let's talk about the fact that people leave horrible things lying around. And let's go on a little bit of a very, very short and simple safari to GitHub. This is in red, so this private key has been deleted, which means I can't see it. So one of my favorite ways to depress myself at night is to go on GitHub and enter the search term delete private key. And then look in commits for people who have made a Git commit, the title of which is delete private key. They could have called their commit anything. They could have called their commit add important feature, and I would never see it. I would never know it was there, because I'm not searching for, you know, idrsa.pem. I'm searching for the words. I'm searching for an admission of guilt. There are 77,821 admissions of guilt. That's a lot of guilt. This guy's my hero. He's done this twice and he still doesn't know that it doesn't work. If you actually start looking into some of these repos, and again, there's 77,821 of them, so there's a lot of commits there to depress yourself with. You'll find a lot of personal repositories with people playing around, and then you'll start to occasionally, every 100 to 200 repos or so, bump into something where you're like, that's probably somewhere important, or like a piece of software that was admittedly by its developer volunteer software written for a veterans hospital, or like various things where you're like, did they stop using that key? I hope they replaced it. I'm not sure. But yeah, definitely some stuff lying around. This is the lowest hanging fruit. This is, I went on the internet and typed some words into a search engine and hit enter, and now I have creds, right? This is barely hacking. This is just advanced Googling. And there's more fruit up that fruit tree, and fruit's delicious. So let's talk about the anatomy of Git, first of all. And we're going to be dealing with like the world's smallest repo. I think we're going to have, at max, at one point, we're going to have a grand total of 5 commits in this repository that we're talking about. I'm keeping it small because I'd like to be able to hopefully have all of you keep what's going on in your head. We're going to try and follow through it, but I want to make sure that as much as possible people can track what's going on. So some of you may have worked with Git at the command line. The basic Git commit to create a new local repository is git init, so we're going to create a new repo, move into that repository. We're going to put the word foo in a file foo.txt. We're going to add that to the index and commit it. So now we've created a new git commit, right, in our repository. In a moment, we'll go to a graph and I'll represent this visually. But for those of you who are command line learners, this is how you add something to a repository. This is the basic, I have created a one commit repository in Git. And that creates something that looks kind of like this, okay? We have at the top head, which is a reference. In your Git repository, there's a folder called .git, and in that folder there's a file called head, all caps. And that file contains a path that points to another file called master under a directory called /refs/heads. And that file contains a hash, contains a SHA-1 hash, which points into a folder in your .git directory called objects. And in that directory, the first 2 characters of that hash are a folder, and the rest are a file, and that's where your commit is. And your commit contains another hash that points to a tree, which is another word for a folder, and that commit contains another hash which points to another object, which is a blob. We'll go into this more, but this is generally what you have in our brand new repository. We have a single commit, which contains a single tree, which is the base folder, and a single blob, which is our foo.txt file. Another way to say this is, like I said, there's a file in a folder called refs heads master that points to a commit. That commit has a SHA-1 sum that starts with ED65AFBF. That points to a tree that has a SHA-1 sum that starts with FCF0BE4D. Points to a blob that starts with 257CC56, and the content of that blob is the word foo. We'll discuss the anatomy of each of these objects. It's not important that you understand exactly where they are. They're all in the .git/objects directory. They're all pointed to by these SHA-1 sums. Git indexes everything. I lie. Git indexes some things by SHA-1 sums until you get into pack files, which is about 2/3 of the way through this talk. This begins to lead us to what I call the original recipe failure to delete, or what we find when we do those fun Google searches for deleted private keys. If I remove my foo.txt file, and then I make a new git commit with the message remove foo.txt, because I didn't want to type the words delete private key, because it makes me sad, we create this. So what's important to understand about Git is that Git does not delete things. It merely creates new things. So previously we had a tree that pointed to a blob. And when we remove that blob from our directory, when we remove the foo.txt file, what Git does is it leaves that tree and it leaves that blob and it creates a new tree. It creates a new commit that points to the new tree and not the old one. And so the old tree and the old blob and the old commit are left behind. This is good. This is it doing what it's designed to do. It's a version control system, and it says that commit points to the old version. This commit points to the new version. And if you look inside the Git objects directory at the hash value of your old friend foo.txt, you'll find that checksum, right? 257cc264, right? That whole thing. It is compressed with the zlib deflate algorithm. So you can use, there's a number of tools you can use. Here I'm using zlib deflate uncompress. I just pipe the object into that. And I get blob 4 foo. We'll take a look at that. But it's there. It's still there in the repository, even though it's not my local directory anymore, because I removed it. In a hex editor, we can actually see what's going on here. We have the type of the file. It's a blob, so 62, 6C, 6F, 62. Then we have a space. Then we have the size in ASCII. Then we have a null byte. And then we have the content of the blob, right? This is a blob object. This is how it's represented in Git. This is the manifest of it after it's been deflated. As for the tree object, it's kind of a similar composition. It says that it's a tree. It has a space. It tells you how big it is. Then it has a null byte. Then it actually gives a mode, which is similar to a Unix mode, but not exactly the same. It's fun to read up on. It's got all of these bytes for the mode, but most of the values are invalid. And then it has the path of the file, right? So it says foo.txt is the path of the file. And then it has that path so that when you do a git checkout, it can restore the file to the correct location. And then it has a checksum, the hash of the object, not in ASCII. Okay? It's important to remember that, because in a moment we're going to look at commits, that hash is going to be in ASCII. This hash is just in binary. So if you're ever looking at this and you're like, why is the hash in this half as many bytes long? When you go to a commit, it's twice as many, because it's in ASCII this time. So commit object, similar. It says it's a commit. It has a space. It tells you the size. Then it references a tree. It says, here's a tree. Here's the hash of that tree. Here's also the author. Here's the committer. And here's a Unix timestamp and a UTC offset, which is fantastic if you're trying to find out where somebody lives, by the way. If you ever want to find out what time zone someone's in, unless they're changing their local time before they do their git commits, that can always be fun. I've been going through these fairly fast. I don't know how many of you may have noticed, but the tree ID just changed. And the reason the tree ID just changed is because when I started doing this demonstration to harvest all these values for you, I accidentally put in my, I had left my Git repository turned on to my work email address. What a fantastic teachable opportunity to show you about how to delete things out of a Git repository. How providential. This brings us to the second way of failing to delete something from Git. Pardon my terrible coffee puns. GitHub has a lovely page on changing the author info. They offer a script to change author info. There's also a commonly used tool called BFG Repo Cleaner. Both of these are wrappers around a Git internal tool called Filter Branch. Filter Branch is designed to allow you to rewrite Git history. In this case, let's pretend I don't really know what I'm doing very well, because that's, as we saw from doing our Google search, most people. I look at my Git log, I see that I have these commit values D21A926, ED65AFB. Those are the checksums of my commits because they're SHA-1 hashes. Everything in Git is a SHA-1 hash, except for pack files. So I run the change_name.sh file. It rewrites the commits. Now they have new hash sums. They have new checksums because something's been changed in them. What's been changed? My email address has been changed. If you go back here, you can see that that commit address, that commit right there, is going to match the one that I had originally. So we've run filter branch. We've changed the values. That's fantastic. And if I look at my Git log, it tells me, oh, we have the right name here. That's not my work email address. You guys all don't get to see my work email address. Now, if I pushed this already, if I pushed this to GitHub, I'm a variable degree of host. And what I mean by say a variable degree of host, if you have a small repository that's private and only you use, you can do a rewrite and you can force push, and you're good. If you've successfully submitted a patch to the Linux kernel, you're never uncorking that genie, and you're just going to have to get new SSH keys or whatever. Yeah, so worst case, big public repository. Best case, small tiny repository, or a corporate repo. Sometimes in a corporate repo, you can tell everyone, okay, you guys have to delete all of your local data. You guys have to delete all your local data and reclone. It'll take you 5 minutes, as long as you've been managing your repos properly. Or it'll take you 6 hours if everyone's committing large binaries into your Git repo like bad children. But let's return to the filter branch we just did, because obviously it solved our problem. That object is still there. My commit object from previous to my filter branch is still there. I've rewritten the history, but once again, the object is still in the objects folder, and it's still there for anyone to see. I've replaced my name and my email for safety reasons. Why doesn't this help? Filter branch doesn't delete anything. It writes new commits, it changes reference pointers, it doesn't delete anything. If you look at the documentation for BFG repo cleaner is going to tell you that afterwards you need to use the standard git gc command to strip out all of the unwanted data, right? It's going to go in and it's going to garbage collect, it's going to remove all of those dangling objects. All right, good, we can fix this. We can fix this. This is going to go well. So we do a git gc. Okay, good. It's done, the git gc, and it says that I can't access the object. Fantastic, we've done it. We've removed the object. Why are there 7 objects? I have made one commit that contains one file and one tree, and I've made another commit that has one tree and no object. I should have 5 objects. Why do I have 7? Let's talk about pack files. The reason that I can't see that object anymore is because when I run git gc, Git happily takes all of the objects and packs them up into pack files. Pack files are basically lists. They're basically binary files that contain pointers into various values inside the pack file, indicating where objects can be unpacked, and they're also delta-fied. So most of Git does not do delta diffing, but pack files do. This is a concession from the Git developers from the very early versions that allows you to transport data more efficiently, right? So when you're doing Git pushes and pulls and you have lots of files that are very similar, files move faster. gzip compression is already pretty good at storage space saving, but pack files are better, right? Pack files do better storage. Best explanation of pack files you're going to find is from the Recurse Center. They explain how these actually work. I'm not going to go into it, but they're very impressive from an architecture perspective. If you wanted to be able to do successful binary search over delta diffs spread over multiple arbitrary files, there's a good explanation in here of how to do it. But you don't need to know how to do this if you want to unpack these files, right? Very simple recipe for dealing with this problem is you take the pack file out of the get objects directory. I just didn't have enough room on the slide for the full hex line. And then you cat it into get unpack objects, get unpacks the objects, and yay, we found the boo, we found the object again. Well, what happened, right? We removed the object. That didn't work. We did a filter branch. That didn't work. We did a garbage collection. The commits aren't in the log, and they aren't referenced anywhere. Why do we still have them, right? If I do get log, these commits aren't here. If I do get log dash dash, oh, they aren't here. Where are they? Let's talk about the get ref log. The get ref log, well, the get ref log command is a command which looks at various logs inside of .get/logs. And the logs are in plain text. You can just read them. You can use this command, or you can read them with any text file editor. What the ref logs actually contain is they contain a pointer to a commit, and they contain a timestamp, and they contain a brief message of what was happened. What the ref logs are is they are a local log of branches and references updated in the local repository. And the head ref log actually stores branch switches. So if you want to see when someone on their local repository is switching back and forth and looking at various branches, if you want to see if your employees are actually, looking between different various branches, you can look at their head ref log and see, you didn't look at anyone else's branch today. You're lying to me, because it would be in their local ref log. And so if you look at the ref log, you'll see there's a pointer. There's a pointer to ref's original ref's heads master. There's a pointer to this old commit, this D21A926. And there's the date of it. It's actually there, Unix timestamp. You can do this in text, or you can actually just use the date raw, and it'll actually give you the full Unix timestamp, just like it's in the git commit. But this is the important thing to remember. Git garbage collect is very friendly. It's not going to delete objects for you that it thinks you might still want. It's not going to delete objects that are still in the ref log. And the ref log, by default, is going to store things for 3 months. Which means, if someone deletes something in the Git repository and you get a hold of that Git repository, even if they've done a filter branch, even if they've cleaned things up, you still have some time. Don't just delete things from the ref log. That will go badly for you. We expire the ref log. We say get ref log expire, expire now. Oh, we say get GC prune now, delete all of the stuff. I don't care about your expiration date, prune it now. Hooray! You run the commands. It still says 7. Why does it still say 7? This is the fourth way you can fail. When we look at the ref log, there's nothing. We successfully expired the ref log. Why are there still 7 objects? When we look at get info refs, there's references to these 2 different refs here, master, which is our main branch, and ref's original ref's heads master, which is D21A926. That's our old commit, right? You remember that? There's nothing in git refs. What are they pointing to? Get packed refs. So if you run git gc before you run your expire, Git will happily pack everything, and it will also pack your refs into packed refs. It generates this single packed refs file because it's easier to transmit over the network. Git ref log, according to my testing at this time, doesn't expire anything in packed refs, so everyone's documentation about how to fix this problem and about how to delete something for your repository doesn't work if a GC has already happened, because the objects aren't going to get deleted because they're still in packed refs. This is easy to notice right now because I have 7 objects in my repository, but if your repository is 13,000 objects long, you are not going to notice that your git gc command has the wrong number. And you are probably not going to check inside packed refs to see if the object is still there. I would bet that there, especially since git gc gets run periodically automatically, I bet there are a fair number of things lurking inside of people's repos that they think that they've successfully GC'd that has been caught by this. Because if you just run these commands out of order or if packed refs gets run automatically, you're never going to see this. So now we have to go in and we have to delete this ref manually. So we do git update ref -d. This will delete the ref for us. And now we do a prune now aggressive. And it's gone. It's finally gone. We finally successfully removed an object from our Git repository, and we only had to fail to do it 4 different times. That's 4 different ways any person can trip up and not delete something. So if you get a hold of a Git repository when you're doing some kind of pen test or site evaluation or breaking into some naughty actor, remember that just because it's not there doesn't mean it's not there. But I said at the start of this talk that I was going to tell you 5 ways to lose things in a Git repo. And these are the 4 ways you can lose things in a Git repo normally. And you say to me, surely this is all the ways we can fail to delete something in Git. And I say to you, my sweet summer child, have I told you about Git notes? Who here knows about Git notes? Yeah, it's widely used, isn't it? Git notes is a fantastic feature that Git has to allow you to add text to Git commits without altering the commit hash. This is a fantastic feature they added because you might legitimately want to go back in time and add notes to a commit that you've already made and store it in the Git repository. In point of fact, Garrett, the Git review software, actually stores, or may have at some point, stores code reviews this way. They append notes to commits. Most other repo management software that I've seen doesn't show these. If you put in Git notes, GitHub used to show them, but doesn't anymore. GitLab doesn't show them. They're effectively invisible. One of the reasons they're invisible is because they're not in a branch and they're not part of the commit. They have their own space and they have their own references. They're stored in refs notes. By default, refs notes commits. And you can push them. You know, I can go back, I can make this note, I can add some classic PII, some classic creds right there. I can have them added, and I can push those notes to my upstream, right? And then I look in my log for that branch that I'm on, the notes branch, and there they are. I can see that Git added notes, which is a commit. That's interesting. Notes are commits? Okay. So how are notes stored? Well, if I check out notes commits, there's a file with the name of a Git commit, and the contents of that file is the note. So the notes commits branch, quote unquote, it's not referenced as a branch, but it functions as a branch. Just contains a series of files with names that are commit hashes. And when Git wants to present notes to you, it just looks in notes commits and says, oh, this commit has a note, so I will display it when I display git log. Well, that's interesting. That has some interesting ramifications. This brings us to way 5, the dangling note. So we're going to create a new branch, git checkout -b, dangling note. We're going to switch to that new branch. We're going to create a text file and commit it, which is very basic, right? And then we're going to add a note. Very simple. Make a branch, make a commit, add a note. Then we're going to delete the branch. We're going to totally delete the branch the right way, the first time. So we delete the branch. We now created something that looks kind of like this, right? We have our master branch, has 2 commits, right? Our first commit where we add the file, second commit where we deleted it. We have the dangling note branch. Dangling note branch has a commit. That commit has a parent that is our second commit on master, but it's deleted. That's why it's grayed out. And then we have our notes commits branch, right? Which has the most recent commit has files in it. One of them pointed at the most recent commit, and one of them pointed at the first commit, right? Now, when I ask get notes to show me the note for that file, it says, I can't show you the note. That's not a valid reference. But if I check out notes commits, it's still there. The file's still there. It doesn't get removed, even though I've removed the branch. The file's still there, the note's still there. Get notes, as far as I can tell, is completely independent from all of the Git's basic GC, reflog, dangling object handling infrastructure. None of it points to it in any way. And remember, you can push them. You can push notes attached to deleted branches. And if you never clean up your notes, you can always clone them. Pull down the notes to deleted branches and read their contents, no matter how long ago the entire branch is expired or been deleted. There is a get notes prune command, right? You can delete get notes. The way it does that is it just looks at all the notes, and then it looks at the hashes, and then it goes through commits and sees if there are matching hashes, and if there aren't, it deletes the note. And that generates a new command. But the way that get notes stores data is completely different from the way the rest of Git stores data. It actually stores these separate files in there, so none of the existing infrastructure for tracking things works. So that is the 5th way that I know of that you can fail to delete something from Git. But let's reflect on this for a moment. Get notes, realistically, isn't that big a deal. As we already discussed, there's one person in here who raised their hand. Nobody uses get notes. I'm not too worried about the credentials that have been stored in there. I'm much more worried about the credentials that have been stored in Dropbox. But the rest of the ways are probably pretty legitimate. It's probably very likely that people are going to delete things using a set of commands and not necessarily go and manually unpack their objects and verify expressly that the objects that they think are deleted are purged from their repository. So if you run across a Git repo in the wild, what should you do, right? First thing, take it, unpack all the pack files, and it's fairly trivially to go through everything and zlib deflate every object and search for credentials through it. Zlib deflate is a very fast algorithm. You can uncompress every single object in the repo in a matter of seconds. There are tools that do this, and I don't want to talk about them, not because they aren't good. They're a general step up from what exists. But the whole reason for giving this talk is for, hopefully, people who may not be familiar with Git internals to walk into those tools with eyes wide open about the nature of the different objects, what it is these tools should be looking for, and how to validate whether or not they're actually finding what they're looking for. There was a talk earlier on today about validating the performance of your security posture. And so when we get these Git scanning tools, we need to take a good hard look about whether or not they're actually picking things out of our Git repositories when they're left there in the various myriad ways that they can be left there. So, thanks all for your time. I'm Jason RtzqO, or RtzqO. I work with DEF CON 562. Thank you. Down in Long Beach. And if you're in the LA South Bay, we'd love to have you come out and visit. We'd love to talk to you about stuff. And if you're not from the LA South Bay and you're just driving through town, we'd love to see you too. Come down, have some talks, do some hacks. maybe go out for alcoholic or non-alcoholic beverages, as is your choice, no pressure. But thanks for watching, and if anyone has any questions, I've tried to leave some time for those and the next person. Anyone? Anyone? Any takers? Any takers? 3, 2. Oh, okay. What? What's up? So, I can't give you recommendations on how to not commit them. I can give you recommendations on how not to push them, right? So the first one's actually really hard. There's not any real, there are local pre-commit hooks, there are ways to do local pre-commit hooks, but that's actually kind of a hard problem, and it's really not, it's hard to manage, because if you're trying to manage that across an infrastructure of staff, you're dealing with the problem of, I have to make sure that no one's tampered with their local configuration on something that's specifically designed to be owned by that user. Right, so the right place to control it if you're talking about enterprise space is control it at the repository with a code management system that actually supports investigating your pushed commits for various kinds of information. Fabricator does this really well. GitLab does this fairly well. But the way to do it is to look at your, to look at your post-commit hooks or to look at your code review tools. I think there's a lot of problems that so-called GitHub flow ameliorates if you're forcing everyone to do their work on their own fork, because your repo management tool supports that, and then they have to pull request all of their code into master. The worst thing that can happen is that they have to delete their fork. And then they can just reclone and start doing work again. You never have to delete all of master because you had someone reviewing all of their commits. That's the human-involved way. But automated code review tools can definitely help here. But they can't do everything, right? Because you set up a rule to block SSH private keys, and then someone commits their Google Cloud JSON credential file. And you're like, oh, well, that's great. That's easy to change. We don't have any automation that uses that that's going to fall over when we rotate that key. Recommend good hygiene with regards to how people get code into your repos is good, but that's on the enterprise space. That doesn't address the question of what do we do for the 77,861 deleted private keys on GitHub. Those are personal repos or community repos. I don't have a good answer for that. Like, GitHub has included tools to try and warn people about this, but AWS has also included tools to try and warn people about public S3 buckets, and that's doing lots of good. So, I mean, every time I go into a client, I see the big yellow box every time I pop open their AWS infrastructure, so it doesn't seem to be helping. Either that or they just never open their AWS console ever, which is probably more likely. This is not alcoholic enough for that part of the conversation.
It's like trying to stop phishing, right? People always find a way to click the link.
Yeah, yeah.
Right? So basically, for example, you because we have protected.
Yeah, they would do that. So yeah, good hygiene is important. And I will honestly say, like, I think I echo a number of security professionals when I say there's nothing that is a replacement for good practices. No level of automation will replace good isolation, and no level of tooling will replace a culture of attentiveness over speed. Because most of these things happen because people don't have the time to do the other way. Like people make accidents happen, right? And sometimes that has to be fixed, but the number of actual accidents of people committing their private keys versus the number of, I need to put this private key in the code base because it needs to go out there with the software because I don't have a password vaulting system. And then 6 months later, we need to get private keys out of the repo. That seems to be far more common. Like the far more realistic solution is organizations don't have infrastructure in place to support good credential management, and then they realize they have a problem, and then they want to retroactively fix that problem, and they go on the internet and they try and fix their problem, and then they still have, at least for 90 days, all of those credentials in their repository. And they're wondering, how did someone get them? Well, they were still in your repo. Dumbass. They're still there. So that's my best answer to that. Anything else from anybody? Anything I explained poorly? Yeah. No, they exist, but I'm not going to recommend any. What? She asked if I could recommend any tools that would scan GitHub for. Right. So I think there are 2 points to that. One of them is there are tools, and my experience has been that they are good at. There are some tools that are fairly good at manipulating the GitHub API, and there are some tools that are fairly good at pulling down repos and scanning them at the surface level. Most of them do not deal with every single way. They don't deal, frankly, most of them don't unpack all of the objects. Maybe some of them are going to go through and look at various diffs of the objects, but most of them aren't going to check out every version of every repo. There are a couple tools that do. But for enterprise purposes, don't use public GitHub. Like that's honestly the best answer is don't do it. It is not, I understand that core driver is we shouldn't do things that aren't our core business, but there are a lot of companies that are more than happy to take on that problem for you that are not github.com. And you know, I really think that's the best solution for keeping your credentials off github.com is to not put them there, not to depend on their ACL layer or their security team, right? They can't be responsible for all of that. There are definitely well-known tools. I'm hesitant to talk about other people's tools generally, unless I'm really confident that they do what they do very well, or really confident that they don't do what they do very poorly through sheer negligence. That middle ground is somewhere I like to keep out of, and so I'm going to say they definitely exist and they will do a fairly good job, but look at them, audit your security tools. Raveen, thanks for calling me by name. Good doxing. Is it your most recent commit? If it's your most recent commit, you can just delete the most recent commit. You can do a git reset hard, delete the objects, you know, and you'll be fine. If it's further back, you're going to have recourse to filter branch because you're going to have to rewrite the history of more, because your most recent commit is only going to have a reference pointing to it, and it's pointing to its parent, but nothing else is pointing to it. But if you're further back, you're going to have to use filter branch because all of the other commits down the chain have to be rewritten to point to the new things. So you're lucky if you just did it because you're going to be able to change that commit, prune the old objects, and move forward. But yeah, it's basically a three-step process. First step, replace the commit. Second step, second step is to expire the reference and get GC. And then check to make sure that you did it right, because you have the commit hash. You have it right there in front of you all along, and now you know how to look. You just look and get objects, see if that hash is still there. Or you pop out the pack file, or you just use git checkout. Just check out the commit directly. If you can check it out and you end up in detached head, it's still there. If it says it's not there, then there's no git commit. So, either of those is fine. Perfect timing. This is when I'm supposed to end. What? Plastic is fine. Okay. Thank you, everyone. Appreciate it.